Entanglement. We're going to talk about the physics of the Nobel Prize of this year, and the speaker co talk is Dr. Hassan Akram, a renowned professor of our department. So please give a round of applause to Dr. Hassan Akram.
Thank you very much for the introduction. As you know that I'm here to talk about quantum entanglement, and specifically I would like to discuss the physics of Nobel Prize 2020, and hopefully I will be able to explain what was the work and what are its implications. You already know that the Nobel Prize in Physics 2022 was awarded to two gentlemen, Alain Aspect, John F. Clauser, and Anton Zallinger, for experiments with entangled photon, establishing the violation of Babel inequalities and pioneering quantum information science. I will not talk about quantum information science, but I will mostly focus on entangled photons and the Babel's inequality. So I would like to start from a very basic and the general concept in physics, the concept of a physical theory. What is a physical theory? By its very definition, a physical theory is something which describes the evolution of a dynamical system. Dynamical system means the system whose state is changing with time. So by definition, the purpose of the physical theory is to describe the evolution of a dynamical system. Now, in my view, a physical theory has to answer three fundamental questions, and then you can say it is logically complete. And once it is logically complete, then you can it qualify for the experimental verification. Okay, so if a theory answers these questions, it doesn't mean that it's a correct theory. Only the experiments can decide that whether it's correct or not. But just to complete its purpose, to fulfill its purpose, to logically complete itself, the physical theory has to provide the answers of three questions. The first question is that how the state of a system is defined. I mean, if you're using certain variables to define the state of the system, then the question is that what are the state variables? The second question is that how the state of the system evolved with time. If your state is defined by a certain variables, which you call state variables, then you can rephrase this question that how the state variables change with time. And the third and the most important question, that how the observables are related with the state of the system. And this third is important because you have to verify your theory. So if the state variables are not related with the observables, then you will not be able to verify your theory. So therefore, your theory must define that how the observable, the things which you can observe, they are related with the state or the state variables. It may happen that the state variable are itself observable, but logically it is also possible that the state variable may not be observable. So in that case, it is extremely important to relate the state variables with the observable. So a physical theory must provide answers of these three questions. What's the difference between classical and quantum mechanics? You already know that classical mechanics and quantum mechanics are two different physical theories because both describes the evolution of a dynamical system. What's the difference between these two theories? The only difference is that both the theories provide the different answers of the same three questions. So classical mechanics and quantum mechanics are different because in both the physical theories, we have the different answers of these questions. So let us first see that how the classical mechanics answers these three questions. The first question, remember, that how do you define the state of the system, or what are the state variables? In classical mechanics, the state of a system of particle is defined through position and velocity variables. So you have a particle or a set of particles in the system, then the state is defined by specifying the position and velocity of each particle of the system. So these are the state variable, position variable and velocity variable, these are the state variable. And how the state evolved, the state of a system, you know, that evolves by following Newton's second law of motion, which says that the net force which is acting on a particle is equal to the product of mass and acceleration. Now, the way it is written, this equation, where we have written this equation, you can easily see that it's a differential equation. It's a second order differential equation in time. And if you want to find a solution of this differential equation, then you have to specify initial conditions. And since it's the second order differential equation, so we require two initial conditions. And what are the initial conditions? You know well. The initial conditions are the initial position and velocity of the particle. So that means that if you know the state variable, which are the state variable, if you know the state of the system at some initial time, then by solving this equation, you can calculate the state of the system at any time later or at any time in past as well. You can also solve in the reverse direction of time. And the third question, that how the state observables are related to the state. The answer is that the state variable are itself observable. You know, position variable, velocity variable, they are observables. And the other observables, they can always be written as a function of the state variable. For example, kinetic energy, angular momentum, all these are observables as a function of the state variables. So these are the answers of the three questions which a physical theory has to provide in classical mechanics. Okay, so what are the implications? By the way, the classical mechanics also tacitly assume that the state variables can be measured without altering them, and in principle with unlimited precision. This is what classical mechanics tacitly assume, because if you do not make this assumption, then the classical mechanics will not be a useful physical theory. If the act of observation alters the state variable, or if you cannot measure the state variable with unlimited precision, then you cannot predict the state of the system at any time t. So we have to assume in classical mechanics that the state variable can be measured without altering them, and we can also measure them with unlimited precision. And what are the implications? As I already mentioned, that the first two implies that if you know the state of the system at any time t naught, then by solving this equation, you can calculate the state at any time later or at any time earlier. Okay, but there are some philosophical implications as well, which we would like to discuss. Now, since we have seen that the state of the system at any time t depend on the state of the system at some initial time, so therefore, we are forced to assume the universe is deterministic. Anything which happens in the universe, that happens because something has happened in the past, okay? Not because you choose to happen it. For example, if you decide to get married, or you decide to choose a particular career, you do so not because of your choice, because of your past circumstances. So that's the philosophical implication. So you're bound to do what you're bound to do because of your initial conditions. So free will, hope, love, they are nothing but delusions according to classical mechanics. So that's the first implication. The second implication, and that's not really an implication, rather I would say that classical mechanics, since it is a deterministic, it says that the state of the system at any time t is determined by the state of the system some initial time, not by the act of observation. Then it means that the classical mechanics is also consistent with the idea that the reality is objective, which means the characteristics of different characteristics of the particles are defined independent of the human observer. So that actually means that the moon exists even if no one is observing it. And if a tree falls in the jungle, then the sound is produced even if there is no observer there. So that's naturally the consequence of deterministic nature of classical mechanics. So these ideas, these views which I'm discussing with you, we are so used to them that we never give them a second thought. And in fact, they are the part of our intuitive understanding of the world around us, they are the part of our common sense. And why they should not be the part of the common sense? Because common sense is evolved by the observation of the objects of everyday life, which satisfy the laws of classical mechanics. So that means classical mechanics is not just a physical theory, it is deeply rooted in our intuitive understanding of the world around us. Okay? But despite all these philosophical implications, it is wrong. So it challenged our intuition, it challenged our intuitive way of understanding the world around us. So this is classical mechanics. And let's not talk about quantum mechanics. As I said, that the quantum mechanics is just another physical theory, providing the answer of the same three questions, but in a different way. So how the quantum mechanics answers these three fundamental questions? The first question is that how do you define the state of the system? In quantum mechanics, the state of the system is defined by a vector, the same vector which we use to specify position of a particle. Okay, but it's a different kind of vector, but it's basically a vector. That belongs to a linear vector space, which is called Hilbert space. And there is one-to-one correspondence between the possible states of the system and unit vectors in the Hilbert space. So these are basically the unit vectors in the Hilbert spaces, which are basically linear vector spaces. The only complication is that they can be infinite dimensional, whereas the ordinary linear vector spaces can only be finite dimensional. So that's why we use the term Hilbert space, but they are just the linear vector spaces which you have studied in the course of linear algebra. So corresponding to every system, there exists a linear vector space or Hilbert space, and there is one-to-one correspondence between the possible states of the system and the possible unit vectors in the Hilbert space. So this is how the state is defined. It is defined by a state vector. And how the time evolution occurs? The time evolution is defined through an operator which is supposed to be unitary operator. So we use a unitary operator, so that means that if you know the state vector, initial state vector, then you can find the state vector at any time t by a unitary operator. Okay, so the third question, how the observables are related to the state of the system. And this question is particularly important in quantum mechanics because you already know that the state vector is itself not an observable. So we must define that how the observables are related to the state vector, or they are extracted from the state of the system. How the observables are related to the state vector. And it is this part of the quantum mechanics which is actually counterintuitive. Sometimes we say that it's difficult to understand. Okay, but it's just because we are so used to the classical way of thinking that these new set of rules, they are counterintuitive. But keeping these intuitive problems aside, but let us first understand that how the quantum mechanics answer this question, that how the observables are related to the state of the system. Okay, so first of all, quantum mechanics say that the observables are Hermitian operators in the Hilbert space H. The Hilbert space, which is used to describe the state of the system. So corresponding to every observable, you will have a Hermitian operator. So there is one-to-one correspondence between the possible observables and possible Hermitian operators in the Hilbert space. And this is important, that the possible values of an observable are given by the possible eigenvalues of its operator. So if there is an observable and corresponding to this observable, you will have an operator, and this operator has, say, only two possible eigenvalues, then only two possible values can be measured. For example, like parity operator, which has only two possible eigenvalues, +1 or the -1. So that means if you measure the parity of the system, the result of measurement will be either +1 or -1. And it's because of this that the quantum mechanics is quantum. I mean, that you have seen that in quantum mechanics, observable can have only certain discrete values. Why is it so? Because the observables, the result of measurements of the observables are given by the eigenvalues of the operator of the observable. And since the eigenvalues can be discrete, and if they are discrete, the result of measurement will be discrete. So that's the reason that why the quantum mechanics is called quantum mechanics. Okay, but let's now go into this more details, because this is just a general statement that what will be the possible values of the outcomes of an experiment. Okay, but now we will like to be specific that what will be actually be the outcome in an act of observation. Now it depends. It depends that whether your state, the system is in a state which is an eigenstate of operator of the observable or not. So let us first consider the case. Suppose that you are measuring an observable and its operator is this, and the system is in a state which is an eigenstate of this observable. So you know eigenstate means that if you apply this operator on the state vector will remain as it is, and you will have a constant factor there that is called the eigenvalue. But if the system is in a state which is the eigenstate, then the result of measurement will be the corresponding eigenvalue. Okay? So in this case, the result is deterministic. You can tell before the act of observation that what will be the result of observation. It will be corresponding the eigenvalue corresponding to the state vector. And after the measurement, the system will remain in the same state. So that means that quantum mechanics says, in this case at least, that there will be no effect of act of observation on the system. The system is in the same state after the measurement as it was before measurement. And the second part, if the system is in a state which is not the eigenstate, then what would happen? Now in this case, the quantum mechanics say there's a random chance of measuring all possible eigenvalues. And there's no way in quantum mechanics through which you could predict that what will be the result of measurement. There's a random chance of measuring all possible eigenvalues, and there's no way through which you could predict the outcome of an experiment. However, the quantum mechanics also say that we can all calculate is the probability of different possible outcomes. The probability of an eigenvalue, since the result of measurement will always be an eigenvalue, so what will be the probability of an eigenvalue? The probability of an eigenvalue will be given by, we call it component of the state vector in the direction of this eigenvector and its square modulus. We call it probability amplitude, when the component of state vector along the direction of the eigenvector corresponding to the eigenvalue whose probability is being discussed here. The square modulus of this probability amplitude will give us the probability of that eigenvalue. So all you can extract from the state vector that what are the probabilities of different eigenvalues of the operator corresponding to some observable. So in this case, the result of observation is not deterministic. Okay? There's a random chance of measuring all possible eigenvalues, and all you can determine, or you can tell that what will be the probability of different possible eigenvalues. And in this case, quantum mechanics say that if you measure the eigenvalue A, then after the measurement, the system will be in the corresponding eigenstate. So in this case, the state will be changed due to the act of observation. Before the act of observation, the system is in the state which is not the eigenstate. We generally call it a quantum state. And after the act of observation, the system will be in the eigenstate. Eigenstate corresponding to the eigenvalue which you have measured. This is called, the collapse of state function. Okay, so you have two situations. I summarize them again. If this system is in the eigenstate, then the result of measurement will be the corresponding eigenvalue, and there will be no effect of act of observation. And if the system is not in the eigenstate, then the result of measurement is not defined, it is probabilistic, and all we can tell is that what is the probabilities of different possible eigenvalues, and in this case, after the act of the observation, the state function will change, the state vector will change, we call it the collapse of the state vector. Okay, so this is the quantum mechanics. Okay? So let's get used to it. I would like to give you some examples of quantum mechanical systems. The simplest possible quantum mechanical system is the one whose Hilbert space is a two-dimensional space. Okay? You can think that why not the quantum mechanical system whose Hilbert space is one-dimensional space? So in case of one-dimensional space, there will be only one unit vector. So there will be only one possible state. Okay, so that's nothing interesting in there. So at least we should have two-dimensional Hilbert space. in which you will have infinite possible states. The basis vector will be 2, but from the linear combination of two basis vector, you can construct infinite possible states. So this is called a qubit. A qubit by definition is a quantum mechanical system described by two-dimensional Hilbert space. So since it's a two-dimensional Hilbert space, and so if I choose the basis vector, which will be 2, say 0 and 1, then an arbitrary state vector will be the linear combination of these basis vectors. And the quantum mechanics tells us that if I measure, say, this 0 or 1, then the probability of 0 will be given by the square modulus of alpha, and the probability of 1 will be given by the square modulus of beta. You can compare it with the classical bit. In classical bit, you have a system which can only be in two possible states, 0 or 1. There is no other state which is possible. But the corresponding quantum mechanical system can be in infinite possible state. It can be in the state, this one, that will be the eigenstate, or this one, or it can also be a superposition state. And since the choice of alpha, beta are infinite possible, so we have infinite possible state in this case. Okay, so the qubit, means a quantum mechanical system with two-dimensional Hilbert space that can be realized in physics or in a physical system through a spin half particle. So how it is realized in case of spin half particle? You know, in quantum mechanics, spin is a very weird quantity. So whenever you have to measure the spin in quantum mechanics, you first have to decide the direction in which you are measuring it. Okay, so suppose that I choose that the direction is z-axis, then there will be, quantum mechanics say that there will be two possible outcomes of observation. Either the z component will be plus 1 over 2 or minus 1 over 2, so that means there will be two basis states in this case. Spin up, this one, and spin down, this one, and an arbitrary state of the spin half particle will be the superposition of these two basis states. Or you can have a photon. A photon can also exist in two possible states of polarization. Either the photon will be horizontally polarized or vertically polarized, so these states are the basis state. So an arbitrary state in the two-dimensional Hilbert space of a photon will be a state which is the superposition of horizontally polarized photon and vertically polarized photon. So classically you say that the photon is horizontally polarized. It's a classical description. The electric field is oscillating along the horizontal direction, and if it is vertically polarized, then the electric field is oscillating in the vertical direction. That's a classical description of photon. Or a Schrödinger cat, which can be a superposition of the dead state and the live state. Okay, so this is the first example. Qubit, mean a quantum mechanical system with two-dimensional Hilbert space. Now we consider a two-qubit system. So suppose that you have a qubit, and these are the basis state in the qubit A, and there is another qubit B, and these are basis states. Two basis states in this qubit and two basis states in this qubit. And let's take a direct product of these bases. So if you take the direct product in all possible combinations, you will get a 4 basis vector, which are in short written in this way. The first letter on the right, that is referring to the state of A, and the second is referring to the state of B. Okay? So we have 4 basis vectors. Now this 4 basis vector can be used to span another linear vector space. That will be 4-dimensional space, and an arbitrary state vector in this 4-dimensional space, which is called 2-qubit system, will be the superposition of these 4 basis vectors. And you can compare it with the classical 2-bit system, which can be only in 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. Whereas the corresponding 2-qubit quantum mechanical system, that can be in infinite possible states, depending upon the values of these coefficients. Of course, you can realize these states as well, but in general, the state will be the superposition of these states. And physically, 2-qubit system can be realized through a system of 2 photons. So the basis vector in this case will be HH, VH, HV, and VV, or a system of 2 spin half particles, right? Okay, so now from here we have discussed so far that what is quantum mechanics, and we have gone through some simple quantum mechanical system. And let's now try to discuss that how the quantum mechanics describes the reality and how it is different from the classical description of reality, which is deterministic and objective. We have already discussed it. So what's a quantum mechanical description of reality? Now, in order to understand or comment on the quantum mechanical description of reality, let us consider a state of photon. We already discussed that a photon is a qubit. I mean, its states belongs to the two-dimensional Hilbert space. So an arbitrary state vector of the photon is some superposition of horizontally polarized and vertically polarized states. And the coefficients in this case, the first coefficient is 1 over 2 square root, and the second is iota over 2 square root. So choice of the coefficient can be complex, okay? But coefficients, as you know, are not itself important. The square modulus of the coefficient is important. So even if you have a complex coefficient, the square modulus of the coefficient will be the real number because they give us the probability, and the probability should be real. So it says that if you measure the polarization of the photon, which is in this state, then there is a 50% probability, because the square modulus of this coefficient is 1 over 2. There is a 50% probability that it will be horizontally polarized, and there is a 50% probability that it will be vertically polarized, because square modulus of iota over 2 square root is also 1 over 2. Okay, so this is an indeterministic state. In this case, it is not defined, that the result of measurement is not defined. Okay, it's a quantum state, superposition state, it's a quantum state. There's a 50% chance that it is horizontally polarized, and there's a 50% chance that it's vertically polarized. Okay, you are probably not very much bothered with this kind of state, in which a photon is in such a state in which there's a 50% chance that it will be horizontally polarized, and there's a 50% chance it will be vertically polarized. You are probably not much bothered by this, and there's a reason for it. Because you are also already used to such kind of indeterministic state in classical physics as well. For example, think of a coin. It's a classical system. You throw it randomly. There's a 50% chance that it will be hit, and there's a 50% chance that it will be attained. Okay? So this classical state is also has same kind of indeterminacy. And since we are used to such kind of indeterministic state in real life as well as in physics as well, so we are not much bothered by this, that in quantum mechanics we also have indeterministic state. But there are some differences. Actually, I would like to discuss two differences in between these two states. So first of all, in case of quine, it is indeterministic, not because classical mechanics tells us. It is indeterministic because classical mechanics tell us that everything is deterministic. It is indeterministic because in this case, in the case of coin which is thrown randomly, you ignore certain factors which determine the outcome of your observation. So which are these factors? For example, when you throw a coin, you ignore the force which you have applied on it. You ignore the effect of air resistance. If you incorporate these factors, the force and the air resistance, then by using the laws of classical mechanics, you can tell that what will be the outcome of your observation. So since the outcome of your observation depends on the force, and it depends on the effect of air resistance, and since you are ignoring it, and since these factors are changing randomly, when you throw the coin again and again, you don't apply always the same force, you apply slightly different force. So that's why the outcome is not deterministic. Okay? So this classical indeterministic state is indeterministic because we are ignoring certain factors which determine the outcome of your observation. It's not intrinsically indeterministic. It is indeterministic only because of ignoring certain variables, right? The force, air resistance. But what about the first state? So quantum mechanics, from the view of quantum mechanics, the state vector gives us the complete description of the reality, the deepest possible description which you can give. And in this deepest and the complete description, it is indeterministic. So there's a difference. The first state is intrinsically indeterministic according to the quantum mechanics, whereas the second state is indeterministic only because we are ignoring certain variables which affect the outcome of your observation. That's the first difference. Okay? And now will you start to bothering about the first state. The second difference is that in case of quine, although the result of observation is not deterministic, but you know, because of the deterministic nature of the classical mechanics, you know that before the act of observation, the quine will be in the head state, or quine it will be in the tail state. Do you have a quine? Can I have a quine from someone? Otherwise, let's pretend that this is a quine. Do you have it? Okay, I will tell you. So this is the quine. Okay. Now, you will agree with me that although we don't know that what will be the result of observation, but we know that beneath my hand, it is either head or tail. So before the act of observation, I can say that it is either head or tail. Okay? But in the first case, you can't tell it from the view of quantum mechanics. Before the act of observation, you can't tell that whether it's a head or it is tail. It is only the act of observation which led the photon to decide that whether the photon is going to be horizontally polarized or it's vertically polarized. So from this you can